In section 13.2, we introduced the concept of the equilibrium constant for the first time. I'm going to talk about two ways of expressing the equilibrium constant, and they are Kc and Kp, and then we're going to talk about how they are related. I'm going to make a second video, and in that second video I will talk about the general properties of the equilibrium constant and compare that to another type of constant called the reaction quotient and talk about how those two things are related. So some reactions achieve equilibrium after nearly all reactants have been converted to products. What we're talking about is that by the time that the rate of the forward reaction equals the rate of the reverse reaction, that most of the reactants have been consumed. So here's a classic example of that. This is called the water-gas shift reaction. And so water is reacted with carbon monoxide to produce hydrogen and carbon dioxide. And this reaction, once it comes to equilibrium, we have mostly products. So reactions where we end up with an equilibrium state where we have mostly products, we say that that system lies to the right. Sometimes we also say it favors products because at the equilibrium we have much more products than what we do reactants. Some reactions achieve equilibrium when nearly all of the reactants are unreacted. So a good example of that is when we react hydrogen with iodine to make hydrogen iodide, and there's only a modest change in the amount of reactants. We make very little of the product. In these kinds of systems, we describe them as the equilibrium lies to the left or favors the left-hand side. And so that's kind of just a little bit of language that you need to be getting used to. Now, what it is noticed for a reversible reaction is that at constant temperature, the same equilibrium state is achieved regardless of the initial amounts of reactants and products. And this is referred to as the law, or known as the law of mass action. What we need to sort of focus in on is, what do we mean by the same equilibrium state? So we really mean that it comes to balance at the same point. So the data for these two experiments will illustrate this. We're going to be reacting water with carbon monoxide to produce hydrogen and CO2. We have two experiments. In the first experiment, we start with all reactants and no products. And in the second experiment, we start with all products and no reactants. And then we let it go and wait for it to come to equilibrium. And at equilibrium, we know we've got there because the concentrations of all of the components will be constant. They'll stop changing. And what do we see? Both experiments arrive at the same place, at the same equilibrium position, even though we started with radically different concentrations of reactants and products. So what it's saying here is it doesn't matter whether we start with 100% products and let it come to equilibrium, or whether we start with 100% reactants and let it come to equilibrium. It always arrives at the same place. So for a generic reaction, A moles of A reacts with B moles of B to give C moles of C and D moles of D. If that reaction is at equilibrium, we could write what we call the concentration equilibrium constant, which we give the symbol big K subscript C. And Kc is equal to the concentrations of the products multiplied together, but each concentration is raised to the power of its stoichiometric coefficient divided by the concentration of the reactants multiplied together, and each of those reactant concentrations is also raised to the power of its stoichiometric coefficient. When we put the symbol of a substance in square brackets like this, that's equal to the concentration, which is given in moles per liter, divided by the standard state concentration of 1 mole per liter, So what we're really saying is that these numbers here are our concentrations in moles per liter, but they're unitless. If the numbers that go into an equilibrium constant are unitless, then equilibrium constants themselves will be unitless. So you get a free ride here on you can't forget to put units in for equilibrium constants because they have none. Some reactions are occurring in the gas phase rather than in solution. So imagine we have a generic gas phase reaction, just like we had before. It's also possible to write the equilibrium constant in terms of the pressure, and we call this Kp, and we give it the symbol uppercase K subscript P. In this case, what we're going to take is the partial pressure of each of our products multiplied together, each of them raised to the power of their stoichiometric coefficient. We're going to divide that term by the partial pressure of each of our reactants multiplied together, and each of these partial pressures will also be raised to the power of the stoichiometric coefficient. The pressures here are the partial pressure in atmospheres, and we're going to do the same little trick again. We're going to divide them by the standard state pressure of 1 atmosphere, and what that means is that we end up with a unitless equilibrium constant. So that's kind of nice because we could see that the units for these things could get really out of hand depending on what the values are for those exponents. So this helps us kind of express the law of mass action in a more sort of useful manner. At constant temperature, we can say the same equilibrium constant K is observed regardless of the initial amounts of reactants and products. So you'll see, however we express K, it is always a measure of the concentration of our products divided by the concentrations of our reactants, or the partial pressures of our products over the partial pressure of our reactants. So a large value of K indicates mostly products. Big K means the reaction lies strongly to the right, whereas a small value of K indicates mostly reactants. So let's kind of think about what do we mean by big and small. If K is greater than or equal to about 1,000, it's almost all products. If K is less than or equal to about 1/1000th, it's almost all reactants. And then kind of in the middle, you're going to get varying mixtures of products and reactants. So here's an example of looking at the law of mass action in terms of the equilibrium constant, and in this case we're looking at the concentration equilibrium constant. So we have this reaction here, it's what we call a dimerization reaction. 2 moles of NO2 are in equilibrium with 1 mole of N2O4. We have 4 experiments, and we have different concentrations initially of reactants and products. In the first case, we have all reactant and no product, and then in the last, and we have that for 3 cases. We steadily increase the amount of reactant, while again starting with no product. And then in the last case, we've got all product and no reactant. So we've got very different, starting conditions. When this comes to equilibrium, in every case, except for the last 2, we end up with very different concentrations of reactants and products. It looks like sometimes there's a little bit more reactant than there is product. It's really hard to, actually it looks in every case as though we have significantly more reactant than product. So we're expecting maybe that K will be small, but we still form some product. So now what we're going to go through and do is calculate K for each of these 4 experiments. We're calculating Kc, that's what was asked for. So it's the concentration of products divided by the concentration of the reactant, and we have to square it because there's two of them. And we do that for each of these experiments here. We're using it's always the equilibrium concentrations that we put into our expression for K. And what do you see? In every case, it's the same number. So this is a fairly small K, and that reflects that we have mostly reactants and just a little bit of product. It's not like that really small K where we have almost exclusively reactants. We've still got, a bit of product there. Okay, so there is a little bit of a difficulty. In most cases, your equilibrium constant calculated using concentrations will not be equal to your equilibrium concentration calculated using pressures. However, it turns out if you know one of these, you can always calculate the other. So here's a reaction where we have 2 moles of nitric oxide reacting with 1 mole of oxygen to produce 2 moles of NO2, and this system has come into equilibrium. And the important thing to recognize here is that on the left-hand side of this expression, you have 3 moles of gas, and they are reacting to produce 2 moles of gas. So as there's a decrease in the number of moles of gas present as this reaction proceeds, and the change in the number of moles of gas as the reaction proceeds towards products will be 2 minus 3. There will be a decrease by 1 mole of gas. It probably seems odd as to why I am mentioning that, but it will come clear in the end. Okay, so here's our reaction. Let's write the expression for Kc. Kc equals products over reactants, so it's NO2 squared, because there's 2 of these guys, divided by the concentration of NO squared, because there's 2 of them, multiplied by the concentration of O2, and there's only 1 of those guys. So that's Kc. Now, it's worth noting that from the ideal gas law, we can express a concentration in terms of the pressure and the temperature. So if you see here, PV equals nRT, dividing both sides by V and RT, so we end up with P on RT equals number of moles on volume, and number of moles on volume is obviously just the moles per liter, or the concentration. So what that means is, instead of writing concentration up here, we can now write P on RT for everywhere that concentration occurs. So now we can rewrite the equilibrium constant in terms of concentrations, Kc in terms of pressure. So just using our little relationship that I showed you before, we do that all the way through. And so here it is here. Remember, I've got to square 2 of these guys because we've got a 2 there and a 2 there. And then the O2 is to the power of 1. And then what I'm going to do is I'm going to pull out this 1 on RT term, just like that. And I'm going to call it, just that's what I'm doing there. So this guy here, he has to get squared. So that's going to become RT to the minus 2. And then I've got 1 on RT squared there, multiplied by 1 on RT. So that's going to end up being RT to the minus 3. Okay, so what I recognize, hopefully, is that this term here is just Kp. Whoa. So what I can write is I can write that Kc is equal to Kp, which is all that stuff, times, and then remembering how exponents work, minus 2 minus minus 3, that would be RT to the 1. So times RT, that's just a constant, right? So what we've got there is Kc equals Kp multiplied by RT to the power 1. if I want, I can reorganize this. Kc multiplied by RT to the -1 equals Kp. Just bringing that guy over there, which is what I've done here. And so now I've got an expression that if I have Kc, I can calculate Kp for this particular reaction. Now, where did we see that -1? Way back in the beginning, I made us do this really odd calculation. I made us calculate delta N. And delta N was -1. Now it turns out, because we don't want to have to do this every time we have a equation for a gas phase reaction, it turns out that Kp is related to Kc through this relationship here. This is that Kp is equal to Kc times RT raised to the power of delta N gas. And something that's important to recognize is that RT raised to the 0 is just 1. So if there is no change in the moles of gas, then Kc is equal to Kp. So you really kind of do these conversions sort of, plug and chug. So here we go, we have this gas phase reaction here. Carbon monoxide gas plus CO2 gas is in equilibrium with CO2 gas. And Kc for this is 3.9 by 10 to the -2. So, this one, it lies to the left. It's going to be, when this comes to equilibrium, it's going to be mostly reactants, but there will be some products around. So the first thing that I want to do is calculate the change in the number of moles of gas. So it starts at 2 and it ends up at 1. So it's always a final minus initial. There's a decrease in number of moles of gas by 1 mole. So now I just apply my formula. Kp equals Kc multiplied by RT to the power of -1. You do have to keep your temperature in Kelvin because it's got to be consistent with your units for the ideal gas constant. And the units that we're using for the ideal gas constant are going to be liters atmosphere per mole per degree Kelvin. So we need those units because we're dealing with pressures and concentrations. So not the 8.314 value, which is what we use when we're dealing with energies. Okay, I put all of that in and I still get a small rate constant. So that's good. If you start with a small rate constant, you should end with a small rate constant. Okay, so that's how Kc and Kp are related. So that brings this first part of section 13.2 to a halt. There's a second video where we look at some more properties of the equilibrium constant and then we relate that to an idea known as the reaction quotient.